Are we ready? Okay. Tutorial 7. So this question, the first question, is actually a source follower. That means to say the input and output is in phase, right? They are in phase, and the gain is always lesser or equal to 1. It has to be smaller than 1 because it's a source follower. And here we are asked to find out the input impedance, output impedance, and the total voltage gain of this stage. So first we do the DC analysis of this to find out what is the VGS and what is your ID, all right, and your VDS to ensure that the transistor is in the saturation region. All right. So let's take a look at how that is done. So I'm not going to write because it's getting too much already. So we're going to go through it. Okay, so the AC analysis of this is by shorting your capacitor. Once you short your capacitor, the input goes directly to the gate. Now in this particular case, you find that there is a resistor link between your gate to the source, which is your 1 mech resistor. So therefore there is a gate current this time, or rather there is a current going in towards the gate. That is because there's a physical resistor link from the gate to source. And once you have this, after shorting the capacitor, you end up with your RG coming in, your RL also linking in parallel with your RS. And therefore now you can do your KCL at this node. You do a summation of current at the source. You find that this current, which is running through your RG, happens to be V in, which is at the gate. Vs happens to be at the output. So Vi minus V out is actually your VGS minus your divided by RG is this current here. You have this other current source from the drain to the source, which is GMVGS. Now GMVGS is GM VG minus VS. Alright, so Vi minus V naught is VGS. Is equal to this current that's flowing through these two resistors, and therefore it's Vs divided by these two, but Vs happens to be V out, so therefore V out over the parallel impedance of Rs and RL. Right? Once you've done that, you can solve this. You find that V naught related to Vi is this value, and therefore the overall gain from input to output is AV, which is given by slightly smaller than 1.874. To find out your input resistance looking in, okay, to find out this input resistance from the gate looking in. Now this is 1 mech. This is 2K, all right, and this here is much bigger. It's I think 100K, all right. Now if you look at this, 1 mech, 2K, 100K. Even if you lump all the resistance up, it is lesser than 2 mech, right? But yet, when you calculate the input resistance looking in, that value is much higher, all right? It's higher than all the resistors that you lump in. Why? Because there is an active component here, GMVGS. And because of this active component, mounted on top of this resistance, you end up having what we call bootstrapping. In this question, they talk about bootstrapping, and therefore, in fact, the input resistance is being bootstrapped to a value much higher, all right, than the total resistance that you see. Okay. Now let's take a look at the output resistance. All right. To find out the output resistance, again, we found that to find out output resistance, you kill the input source. So you kill Vi. When you kill Vi, what happened? When you want to find out the output impedance, you apply a fictitious voltage source and measure the current going in. All right. The fictitious voltage source, which is Vx, is going to be applied across VGS. Therefore, VGS and Vx are related. All right. In fact, Vx is minus VGS. All right. So that's why you have minus here. and therefore we can again find out the summation of current at this node. Ix is equal to the current here, and the current here, and therefore you have this three term here equating it to Ix, and therefore you can find R out, basically dx over Ix given by 247 ohm. Okay, so that is your R out. To find out your, and then in the part B of the question, it asks, in order to have the gain equal to 1, now the gain is 0.874, but if we want to boost it to a value of 1, what can we do to do that? In order to do that, if you look at this, in order to make the gain equal to 1, that means that the signal coming in, the gate must be equal to the signal at the source. And therefore, the input impedance must be infinite in order to have zero current flowing, right? And therefore, the voltage here will be equal to the voltage here. And that is why we have this, right? So if this is basically a buffer, right? Remember op-amp as a buffer. The input impedance must be very high and the output impedance must be very low. It's a impedance transformer. Now, a source follower is basically a one-stage buffer, all right? A one-stage buffer, all right? That's why, in order to do that, we need the input impedance to be infinite. Okay? Any question? No? Let's take a look at question 2. So, the days of one transistor is over. Okay? From question 2 onwards until the end of this semester, there will be more transistors that you can have. Alright? So starting from question 2, you see transistors that are much more than one. If you look at this stage and this stage has the same DC condition. Why same DC? We remove all the capacitor. When we remove all the capacitor, we see one transistor, same as this. Same biasing, same collector resistance, same emitter resistance. The sum of these two is the same as this single one. So therefore the DC conditions are the same. Alright? And therefore you only need to do one DC condition, and that DC condition applies to this as well. Okay? However, the AC gain is different. Why? Because the AC gain of this stage has included this resistor, because this will be shorted out. The AC condition for this stage has this resistance shorted out. Right? So the two AC conditions are different. Therefore, the gain of these two states in AC will be different. But the two DC conditions are the same. Okay? Let's take a look at how this circuit is being analyzed. Okay, so in question 2, we have two identical DC conditions and two resistor, another two at the collector emitter, and therefore we can find out the Thevenin's equivalent at the base. VB is the Thevenin's voltage, RB is your Thevenin's resistance. The two resistance in parallel gives you your Thevenin's resistance of 11.25K, not 11.3. Your VB, which is the voltage at the base, is a potential divided voltage of VCC to this node, and therefore is 180 divided by the sum of 300 and 180. That gives you 112.5. And then you can do this loop equation here. So in this loop equation, you find that VB must be equal to the voltage drop here plus the voltage drop of 0.7 plus the voltage drop across the emitter resistance. Alright, so therefore you can write VB is equal to IB times RB plus 0.7 volt plus beta plus 1 IB times RE, and when you rearrange it, you end up getting the equation out in IB. So IB can be found to be 2.13 microampere. Once you find out IB, you can find out IC, because IC is beta times of IB. You can also find out IE, because IE is beta plus 1 time of IB, and therefore this three current is known. Once your three current is known, we can find out the VCE across this transistor because we know VCC. If we take VCC, we subtract the voltage drop across RE and RC, the remainder will be just VCE. Alright? So therefore VCE is found to be 5.71. Now this voltage is obviously much higher than 0.3 volt, therefore the transistor is in the active mode of operation, which implies that this is forward bias. This is hello? What's happening? Reverse bias, right? When a transistor is in the active mode of operation, this junction VCB is reverse bias, this is forward bias, right? This too will become forward bias when the transistor is in saturation. Alright? Okay? So this is just to help you to identify that the transistor is in the active mode of operation. Right? Once you have done this, since you have found the Q point, you can now go ahead and find out GM, R pi and R naught. Now GM, R pi and R naught are all given to you. The formulas are given to you for your exam. Huh? So these are things that are given to you. Huh? Alright? So therefore once you have found that, you can now do your AC analysis. So the AC analysis would look like this. Okay, so this is your AC equivalent. You find that the first stage, you have a resistor, 2K. 18K is being shunted out, so you have 2K. Second stage, no emitter resistance because the 20K is being shunted out. So you don't have an emitter resistor here. And you have your two stage here. Alright, so we are asked to find out the input resistance. So therefore, with that, we can find out your input resistance. This is your Thevenin's resistance for your two-stage input, first stage and second stage Thevenin's. To find out your input resistance of right for this entire amplifier R in, it is RB in parallel with R in prime. Huh? Now R in prime is R pi plus RE referred to the base. Huh? RE, when you refer to the base, you multiply by beta plus 1. Sum it up with your R pi gives you your R in prime looking in. Huh? So R in prime when it goes in parallel with RB1 gives you your R in. Huh? Alright? And therefore you get the value to be 73.6K. Now you can find out your overall gain. Now overall gain is equal to your two-terminal voltage gain. Your two-terminal voltage gain is between the base to the collector. This is VT1. From the base to the collector of Q1 is your VT2. So AVT1 times AVT2 gives you your terminal voltage gain of this two stage. And then from your input to your base of the first stage, you have an input attenuation factor, which is Rin divided by Rin over Ri. And that gives you a total voltage gain. Okay? So from here, you can now go in and find out each of your terminal voltage gain. Okay? So to do that, we can now find out what is the first stage terminal voltage gain. So the first stage terminal voltage gain, taking the voltage at the collector divided by the voltage at the base, that is your terminal voltage gain from one terminal to another terminal. Right? So voltage at the collector is equal to the current that's flowing through these two resistors to this node, right? So therefore, the current that's flowing through these two resistors comes from the collector of this transistor. So it's the collector current. So the collector current is related to the base current, beta times IB. Yeah? So that's your collector current. Collector current multiplied by these two resistors in parallel, divided by the voltage at the base. Voltage at the base here is equal to the base current multiply the total resistance looking into the base, which is R pi, plus Re referred to the base, Re referred to the base, And therefore this is the total resistance seen looking into the resistor base. Multiply by the base current gives you the voltage at the base. So when you take a look at this, you cancel the base current, and therefore you evaluate, you find that the gain is minus 3.1. Realize that the gain is not high, it's very low, it's only 3. Yeah? Minus to show that this is an inverting amplifier. Right? Between the base to the collector, there is an inversion, right? There's a 180-degree out of phase, so there's a minus here. Right? And the gain is not high. Why? Because there's an emitter here. Right? There's an emitter resistor here. You will see in the second stage the gain is much higher because there's no resistor at the emitter. So take a look at the second gain stage, EE2002. It is the voltage at the collector, which happens to be the voltage at the output, divided by the voltage at the base, which happens to be the voltage across R pi 2, which is VBE2. And therefore we can write the equation for AVT2 as the voltage at the collector. Voltage at the collector is due to this current flowing through these 3 resistors. So these 3 resistors are in parallel, and it is being serviced by the same current, GMVBE2. So GMVBE2 multiplied by RL prime, which consists of these 3 resistors in parallel. Alright? So when you multiply out, cancelling the VBE, you get the voltage gain of minus 147. Realize that the gain is very different. Okay? Even though the DC condition of the 2 stages are the same. The DC condition of the 2 stages are the same. Correct? And yet, the gain is so much different. Why? Because there is no emitter resistor here. Alright? And therefore, when you multiply by the 2 gain stages plus the input attenuation, you find that the gain is very high. Is surely die. Okay? Any question? Okay. Then we take a look at the output impedance. Alright, to find out the output impedance, again we look into the collector, omitting the load resistor, just look into the collector, including your collector resistor and the output of the collector of the transistor. And therefore when you look at it, you find R0 and RC2 in parallel. And therefore you can work this out to be 18.8K. When you are dealing with output impedance, you kill the input source. So when you kill the input source, there's no current flowing here, there's no current flowing here, alright? And therefore VBE is dead, no more. So this current source is not there, the voltage here is 0, the voltage here is 0. Sorry, therefore there's no current source, therefore you only see these 2 resistors in parallel. Okay, and that is your output impedance. Okay, any question? You guys have to understand it. Don't just look at me blabbering here. Any question now? Or you just think, okay, I can always go back and read. Don't do that. By the time you are ready to read, it's very close to the exam. Alright? And by that time, you have so many things to read, so many things that you need to understand. Not the good time to do it. Do it now. Okay? Start doing it now. This is a 4AU course, so it's not a joking matter. Realize that from next semester onwards, the course is going to be bootstrapped even higher. Why? Because the lab is coming into the EE2002 as well. So the CA condition would increase to 40% with lab included. Okay? Just to give you an idea of what is going to happen next. Okay, let's take a look at question 3. Now this is question 3. Realize that just now we only had 2 stages. This one is 3 stages. Now, in the exam, most likely, or rather, in the exam, when you look into multi-stage, the DC condition will not be asked. You will be given the DC condition, all right? You only evaluate the AC, all right? But in those single stage question, DC analysis will be there, all right? So you will have to do DC analysis plus AC. But if it is multi-stage, you will only do AC analysis, okay? So let's take a look at this question. It has 3 stages: first stage, second stage, third stage. The first 2 stages, non-identical. Even the DC condition is not the same, all right? So you have to do everything one by one. First, do a Thevenin's equivalent, get the Thevenin's voltage, find out the base current or collector current or emitter current by the DC loop equation here. Find out the DC current, get the VCE to find out whether the transistor is in the active mode of operation. Take this, put it in your pocket, do the second stage. Do the Thevenin's equivalent of the second stage, do the Thevenin's resistance of the second stage, do the loop to find out the DC condition, to find out the Q point, find out the R0, R pi, and GM. Take everything, put in your pocket, do the third stage. Do your DC analysis here, get your Thevenin's resistance, Thevenin's voltage, do the loop, find out your VGS, find out your ID, solve for the Q point, get your GM, you get your DC condition, then you do your AC analysis. After you do that, this is what is going to happen. Okay, so we first do the DC analysis, get the Thevenin's voltage, get the Thevenin's resistance, find out the collector current by doing this loop. All right. Once you found out the collector current, take the other loop from VCC towards ground to find out your VCE. VCE is found, and you see that this VCE is definitely much greater than 0.3 volt. Therefore, the transistor is in the active mode of operation. And you have your Q point. You have your IC and your VCE, your Q point. From there, you can find out your GM, your R pi, and R0. Again, these are the only thing that the formulas that you'll be given. Then you do the second stage analysis, DC analysis. Again, you do the Thevenin's equivalent. You find out the Thevenin's resistance, Thevenin's voltage of the second stage. Find out the collector current or the base current or the emitter current, because from each of that you can relate it by beta, and therefore you find that the collector current is 1.27. From there you can find out your VCE, because you can take the loop from VCC down to ground, removing the voltage at the collector, removing the voltage at the emitter, you get your collector to emitter voltage. Now looking at this again, the transistor is in the active mode, and therefore you know your Q point. From there you find out your GM, R pi, and R0 by the equation that is given to you. Okay? Once you have done that, do the third stage analysis. Alright, so in the third stage analysis, in this particular case, the DC analysis is already being given in tutorial 5, question 3. Alright, this is question 5. This is question 3 of tutorial 5. And with that DC analysis, you can find out your GM, your R0, and so on. And from here, you can now go and do your input resistance sheet. Having the resistance for RB1, RB2, and RG3 given, or rather found, you can now go and find out the input resistance looking into this equivalent AC circuit. So in this equivalent AC circuit, if you look at this particular stage, you'll find that all emitter resistance is being shunted away by the capacitor. So there's no emitter resistance, alright? And therefore the gain of each of this stage is going to be higher, right? And again, to find out the input resistance, R in, when you look into this, is actually RB1, which is the Thevenin's resistance, in parallel with R pi 1. That gives you R in of the first stage. That gives you to be 7.18K. Now, since both stages are fully bypassed emitter fully bypass common emitter amplifier, then the gain is going to be high. Huh? Let's take a look at how you calculate the overall gain. So the overall gain is given by input attenuation multiplied by the 3 stages of terminal voltage gain. Huh? Alright, so you end up with AVT1 times AVT2 times AVT3 times the input attenuation that gives you your overall gain AV. Okay, to find out each of the AVT, so the first stage AVT is equal to, looking at this AC circuit, alright, so if you look at this, to find out your first stage terminal voltage gain, that is between the base and the collector. So the gain between these 2 points, so VC1 divided by VB1, that is your terminal voltage gain of the first stage. So now VC1, the voltage at the collector here, is equal to this current flowing through this 3 resistor. Right? So this current is GM1 VBE multiplied by the T3 resistor that is in parallel. So you end up with this. Divided by the voltage at the base. The voltage at the base happens to be the voltage across R pi, which is VBE1. So therefore VBE and VBE cancel. And you can find out the gain is minus 21.45. Minus because it's a common emitter configuration. The gain is inverted between the input and output, 180 degrees out of phase. Alright? Second stage gain, same thing. Voltage between the collector of the second stage divided by the voltage at the base of the second stage. Collector voltage is this current going through these 2 resistors. This 2 resistor is in parallel now. Alright, they are in parallel. Coming from this current GMVBE2, right? Divided by VBE2, which is the voltage at the base, which is across R pi 2. And therefore again you cancel out your VBE. You end up with a gain that is minus 219. So when you take this 2 and multiply, you find that the gain is very large. And to find out the third stage common drain configuration, now this comes from tutorial 6, question 2, right? And therefore you can find out the gain, and the gain of which is this. Alright? You find that the voltage gain at the third stage is the voltage at the source divided by the voltage at the gain. So voltage at the source, which is this node, is given by this current flowing through this 3 resistor. So GM VGS3, which is the current source, multiplied by the 3 resistor in parallel, divided by the voltage at the gate. Now the voltage at the gate is this voltage is equal to this voltage plus the voltage drop across, or rather the voltage drop across this VGS plus the voltage at the source towards ground. So voltage at VGS plus the voltage from the source towards ground, which is this current, or rather this current flowing through these 3 resistors. So you end up with this equation. Get rid of VGS, you get this equation, substitute the value, you find that the gain is 0.31. Realize that that value is smaller than 1 because it is a source follower. The voltage the gain has to be smaller than 1. At the largest, it is 1. Okay, it cannot be more than 1. It is always in phase because the source follows the gate. Alright, so it is in phase. Right, so the total voltage gain is the first stage gain multiplied by the second stage gain multiplied by the third stage gain multiplied by the input attenuation. That gives you 610 volt per volt. Okay? And to find out the output resistance looking in, okay, to find out the output resistance, you remove this resistor and apply a voltage at this node, Vx, and this voltage applying here will provide a current Ix. When you're looking at the output impedance, you kill the input source. When you kill the input source, this node goes to ground. Correct? When this node goes to ground, VB is 0. Right? VB is 0, but VE is also 0. This current source is also gone. So there's no voltage here. If there's no voltage here, VBE is also gone. This is gone. VG is also gone. So what happened? You only have these two resistors in parallel, right? These two resistors in parallel. And therefore you have R03 and RS3 in parallel. And that gives you your resistor, output resistance to be 434 ohm. Okay? And you want to find out what is the minimum voltage, or rather the maximum voltage at the source of your third stage, your gate to source voltage at the third stage. So this value must be greater, must be smaller or equal to 0.2 into VGS minus VT. That equation has been solved. I think Prof. Chang has derived that. All right, and basically it's using the square law, removing the square term, right? When you remove the square term, you find that the small VGS must be smaller than this value in order for the output current to be related to the input voltage linearly, right? So you remove the second order term. Just like in the case of VBE, because of the exponential function, we remove the second order, third order term and equate e to the x equal to 1 plus x, right? The same way as doing that, we end up with this equation. So in this equation here, we are asked to find out what is the what is the voltage at the gate to source such that it is linear. So therefore, we relate this all the way to the input voltage by taking the input voltage, substituting into your VG3, because we can relate VI to VG3, and therefore we end up with this equation. Taking this equation, equate it with this equation, you have this equation here, and therefore you can find VI must be smaller or equal to 218 microvolt in order to be linear, in order that the output voltage is linear. Alright, so we end up with this equation. Now, this is referring all the way to the output VGS. Now we have to relate it to the second stage as well. So to find out the second stage, we found that VBE must be smaller than 5 millivolt. Correct? Anything more than 5 millivolt, the transistor becomes nonlinear. Alright? So therefore, again, we have to relate it to the second stage VBE. Now the second stage VBE, when we refer it to the input VI, it is related by AVT times the input attenuation times the input voltage must be equal to a small VBE of second stage. And if you relate it, it is 8.97 VI is equal to VBE2. Now VBE2 must be smaller than 5 millivolt, and therefore you can substitute this into this. You find that VI must be smaller than 557 microvolt. Now, which one is dominant? Should VI be smaller than this value, or should VI be smaller than the previous value which we found, 280 microvolt? Obviously, 280 microvolt, because 280 microvolt is smaller than this value, right? Alright? So if we use this, we will get the linearization all the way to the second stage. But from the second stage to the third stage, it will be, the value will be too big for the last stage. Alright? So to ensure that all three stages remain in the linear condition, VI has to be smaller than 280 microvolt. Okay? Any question? Any question? No question.